Thank you. Thanks. Thank you for coming. It's my first time publicly speaking, actually, so I hope it will go fine. Like Dan said, I would like to talk about today about hashing. If you're familiar with the concept of this, I don't think you will know any new things, because I try to make this presentation as basic and as easy to understand as possible. So hopefully, if you're not aware of these topics, then you will learn something new. So first, let's see what's in the agenda for today. Firstly, I will do a short introduction to the topic. Then I will go into theory, not much of theory, but we have to cover some of the theory that's to be done. Then we'll go into example usages where these hashing functions can be found. Then we'll go into a security aspect of this, because they are used in the important parts of the many systems, and we also go into security aspects. In the end, I will show the live, maybe not live, code examples, how the hashing functions can be used in our everyday work. And in the end, I will do some short summary. So, when I was preparing the introduction to this presentation, I thought about cars. Why about cars? Because I think they are similar to the hashing functions. How? First of all, we know how the cars works. We know that there's a steering wheel, a wheel for wheels, gearbox, pedals, etc. We know how it's working. It's not secret knowledge. Also, there are different types of cars. There are regular cars to commute from place to place. There are buses to move many people at the same time. There are trucks to move big transports. Also, I don't think you should try at building your own car. Of course you can, but it's a really difficult task. And unless you have some kind of experience in that place, you shouldn't do it. And you could, in theory, drive a car without any driving license. It's illegal and it's not advised to do, but you could do it. And I think there are many similarities to the hashing functions, because most, if not all, of the hashing functions have open implementations. You can look up the algorithms and go step by step and see how they are working inside. There are different types of hashing functions. One, they are fast. The other are reliable, and they have different users examples. Also, you shouldn't try to create your own hashing functions, because they are quite key aspects of your software programs, and they can't be rushed in development. And I think that they are similar. So, going to the theory, let's imagine we'll try to define what is a hashing function. But first, let's imagine we are in the hotel. This hotel is maybe not the greatest representation of the example, but because our hotel has only 10 rooms, but I think they are pretty spacious rooms, so that will do. And in this hotel, there is a computer that assigns room numbers to the guests. So if a new guest is coming, he just goes to this computer, inputs his name and other data. The computer thinks, and after some time, this computer puts out a room number. So in this example, first guest goes into room number 7. If we do this 9 more times, we'll have something like this, probably. And basically, what we've created is, technically speaking, is a hash table. But what computer was using was a hash function. So, in terms of technical terms, it meant that this function took an input, in this case a username, and output some kind of value. In this case, it was value range from 1 to 10. But in other examples, in usual examples, this number should be quite bigger. Or it can be some kind of string of fixed length. Also, not every function can be called a hash function, and not every hash function is good hash function. And what properties should good hash functions have? Let's see. There are 4. First one is determinism. Every time we put the same input to this hash function, we should get the same result, because we are relying on this determinism in the long term. This hash function will be used many times maybe in short term, and we have to be sure that the outputs are reliable and we can trust them. The second property is this function should be one-way, so there is no possibility to reverse this process. So if we hash a value, there is no reverse function that will unhash this value. So from only seeing the hash result, we can't see what was inputted in the first place. The third one is the range should be defined. So the output of this hash function is well defined. In our hotel example, it was range from 1 to 10, but like I said, it should be bigger. In the programming environments, it's usually some kind of integer number, or like I said, a string of fixed length of characters and numbers. And the fourth one is uniformity. This handles the probability of appearing each of the results. So if we come back to our hotel example, we've got 10 rooms, and if any guests come by, there is an equal probability of getting each of this number as a result. Of course, there are functions that has to have more strict rules as this one, and also there are functions that have more properties than this, because they are used, for example, in security, and secure hash functions have to have more properties. Okay, so what's exactly happening inside each of these hash functions? I won't go into much details in this case, because every function has different implementation, but what we can do is create some kind of skeleton of each hash function, and processing of each hash function has 4 steps. First one is initialization of variables used in the process of hashing. It can't be the empty strings or 0 number, it has to be some predefined value for easier implementation. Second one is padding of input. We have to make the input the same size, or the size that is accepted by each of the hashing function. It's usually some kind of power of 2, 512 or something like that. There is also some data about length of the input, and the rest is padded with 1s or 0s because of the third step. In this step in loop, we are making some kind of bitwise or modulo operations on the input. Why? Because they are fast in calculation, and also they are hard to reverse. And bitwise operations are also implemented hardware, so they can be easily used in the most smallest and easiest machines. And the fourth and the last step is concatenating the results. So if we are done with the hashing of parts of the input, we are concatenating the output, and we give it this output to the user or caller who called this function. In our case of our hotel, we've got only 10 rooms. But what happens when 11th person comes? Do we kick this person out, or should we just do something else? This problem also happens during the hashing, and we call this situation a collision. That two person is going to one room, and there are many ways to handle this situation. And even in our small example, it was quite easy to imagine. We have 10 people and comes 11th. It's quite small. But even in the larger scale, for example, if we have every integer number, for example, in the programming sense, it also can happen, and it happens quite frequently. And I will try to show it why that's happening. but we have to move from the hotel example to the birthday. Let's imagine this problem. We have n people, n amount of people. How many people do we need minimally to at least 2 of them having the same day of birth? We're talking only about month and date, not about the year, because it would be too much to handle, but only about day and month. How many people do you think it's minimal to have at least 2 with the same date? Any guesses?
It was around 20.
Yeah, we'll go into it, but to be sure that we have. Okay, the obvious answer is 367, because we have possible 366 dates in the year, including the 29th of February. And when we get the next, and we have let's imagine the worst case example, we have 366 people, and each of its person have the different dates, so from 1st of January to the 31st of December. And when the next person comes, it has no possibility, it has to be the duplicated date. But it's not the answer we're looking for, because, interestingly enough, we only need 23 people to have a 50-50 chance of this happening. And more interestingly, we only need 70 to have almost certainty of this happening. This is the graph which shows the maths behind this. There is some kind of equation behind that, but I won't show it, and I can't remember what's in it. But it's clearly, we can clearly see that the point with 30%, 50% is about 23, and this 70 is almost 100. This is called a birthday problem or birthday paradox, and it can be used to crack the weaker hash functions. It was used in this cracking, but most of the modern hash functions should be resistant to that kind of attacks. So, how we can handle collisions? I will present 3 methods, but there are many more. These, I think, they are the easiest to explain and the most popular. The first one is called separate chaining, and we're back to our hotel, and as you can see, the hotel is full. We've got 10 rooms and only 10 people located there. We still have the same hashing function, the same computer, but the new guests come. He probably hates his life right now, because yeah, full hotel. And then the smart manager of the hotel comes and says, okay, we're changing the rules. Instead of 1 person per room, we can now have multiple persons per room. So we have to change the representation of this hotel. So instead of 1 person per room, now we have a list of persons per room. And now, if this guest input his name in the computer will output some number. Of course, it will be from the range of 1 to 10. In this case, it is also a 7. There is a person in room number 7, but it's not a problem for that. For us, we only add a new person to this room. So yeah, that's the method. Second one is called open addressing. The situation is similar, but we have some free rooms, and some of these rooms aren't free. The next person comes, input his name, and gets number 3. Room number 3 is not free, but there is a rule in the hotel that if the room is not free, you should look for the nearest free room in the vicinity of this set number. In this case, there is a rule that we have to search 1 by 1. In this example, room number 4 was free, so this person goes into room number 3. But we can do another things, like in this case there was 1 by 1, but also for the optimization features, we can go by solving some kind of quadratic equation that will speed up this process, and we will find the free room quickly. Or we can use some other hash function that will calculate the next room to look for if it's free. And the third one is called cuckoo hashing, obviously. It's a type of open addressing, but with some small twist. Let's go to the same example as open addressing, but in open addressing we had skipping one by one, and in this cuckoo hashing we have a hashing function here that will calculate the next step. If it's free, okay, then let's put this guest in this room. If it's not free, then we will have to calculate another hash function that will show the next step, the next room to check. There is predefined amount of these hash functions. It's many hash functions. If all of these functions fail, then we will have to do some rearranging of the current rooms, and it gets messy. But the basic premise of this cuckoo hashing is that we're going through the rooms with the many hash functions. Okay, so after collisions and theory, let's go to the usage. How and where these hash functions are used. The most basic usage that I pretty much showed you is hash tables. These are the hotel example was basically a hash table. That's a set of pairs when the one element is the input value and the other element is the room number. That's basically it. We can look through the inputs and look where in the output they are located. The other feature that uses hash functions is cache. If we are keeping a temporary data which could be removed after some time, we don't usually have to want to keep it in full plain text. Sometimes it's easier for us to keep it as a hashed value just for comparison. We don't need to see if it's completely the same, but we only have to check for hashed values, and we can compare if we can contain this data in the cache. We can also use hash functions to find duplicates in some sets of values. Instead of comparing the literal values of the elements in the table, we can just calculate their hashes and count how many hashes are duplicated, and then we know which values are duplicated, and we just then go to the real example, real values, because we have this pair of real value and hash value. Also, we can find similar values in the lists. Some functions have this property that similar inputs give similar outputs, and the same. If the inputs are long, we don't want to compare these complete inputs of, for example, thousands of characters. It's costly and it takes time. Instead of that, we can just calculate the hashes, which are much shorter, and we just can compare the hashes. Some functions provide this feature that the similar hashes are from similar inputs, but not all of them. But these functions can be used to find similarities. And the last thing, which I will spend more time on, is cryptography. This special set of functions are used in like logging in on the passwords, etc. And now I'll try to tell something about them. Apart from the four properties that I showed previously, these cryptographic hash functions have to have more properties. They have to be calculated quite fast, because logging in is quite an important part of the system and should be done quickly. No one wants to wait for the hash function to be completed. The second one is the so-called avalanche effect. So I previously stated that some functions provide that similar inputs give similar outputs. In this case, we have to provide the opposite. The similar inputs give the totally different outputs. The rule is that at least 50% of characters of outputs have to differ. And the third one is impossible to find a collision, so there is no physical possibility to find a collision. It's with the asterisk, because it's possible, but the calculation time is so long, and the probability and the resources also would be too much to handle this kind of looking for collisions. Okay, so where and how these cryptographic functions are used. Like I said, they are used during the login procedure. Usually when we are creating some account, we've got this kind of registration form when we input our username and our password. And what's happening behind the scenes after we click register, there is created a pair of my username, my login, and my hashed password. But how this hashed password is created? The actual password was this simple string, admin123. To this password, we added a random string. It's called salt. And this random string was concatenated with the original password. And on this string, we executed the hashing function to create our hashed password. And this pair of login and hashed password is stored in the one database, and the salt for this login is should be stored in other database for the security measures. It can also be used as a file verification method. Let's imagine we are waiting for an invoice from our, for example, mobile company, and we are getting this invoice via email, and it's a PDF file, for example. We can calculate the checksum of this PDF file just executing hashing function on this file. It's converted into the string of numbers, and some checksum is being created. We also receive the second email on some other way, not with this invoice. We are receiving also this actual checksum. So the mobile company is sending us what was the checksum on their side, on their invoice. And we can compare these checksums. If they match, then okay, that's the same file that our company sent us. But what if somebody intercepted this file with the invoice and sent this one the wrong file with the, for example, wrong value or wrong bank account number? Then we immediately will know that there is something wrong, because when we check the checksums of this wrong file, the checksum will not match the one we received from the company, and we will know immediately that there is something wrong. Okay, so talking about security, let's see how can we possibly break these hash functions. We could try to find a collision. So let's find an example of the value of the input that gets the same output. For example, in our case, I've inputted a password admin123 and get some kind of hash. Let's find another value that will get us the same hash. It's difficult, but that's one way of the cracking this. The other way would be to trying to reverse the hash function. So we have the output, and we're trying to do some kind of operations to reverse it and see what was hashed in the beginning. Also, we could try to brute forcing it. So we will iterate through each and every possible value of the input, and we will compare it with the output, and we will then see if they are matching. It is also a costly procedure, and it will take a lot of time. Like I said, you shouldn't try to do your own hash functions. We should trust others that do it. There are many people that they are experts in this case, and they spend many time and many experiments are being done just to be sure that the hash functions that they are providing are secure and they are worthy of being used. This table shows the example of two hash functions. One is SHA1 and second is SHA512. I've used two sample inputs. They differ in just one letter. The first line ends with the G and the second line ends with the S. And I don't know if you can see, but the outputs of both of these are quite different. And also the length of the outputs are fixed, but they are also different than the input. Input was 28 or 29 length, and the output of the first function is always 40, and the output of the second function is always 128. So like we can see, there is no possibility that we can, only from the output, that we can determine what's the length of the input. We can determine what characters was in the input, and also if the input is similar to the other input that we for example cracked in the other way. But let's imagine that we would try to crack. We want to crack this problem. And we are trying to brute forcing it. So we're iterating through each and every possible input and looking at the output. Let's try to calculate how many operations it would take. So this is a bit of a math. Let's imagine that we are allowing in our inputs only small letters, capital letters, and numbers. In total, it's 62 characters. Then we'll go through each and every possible length of the input. So, for example, there is 62 different strings of length 1, 62 squared strings of length 2, etc. To go through all the inputs from length 1 to 5, it's over 900 million of inputs. And it's only from length 1 to 5. Usually passwords should be longer, at least 8 characters, and also they should contain some kind of special characters. So the number 62 will go probably higher, and these results will be useless because they are not possible. So these numbers they grow quite fast. The calculation of all inputs from 1 to 10, of length from 1 to 10, is 8.5 times 10 to the 17th. And from the 8 to 15 is 7.8 times 10 to the 26th. And to compare, the age of the universe is 4.3 times 10 to the 17 seconds. So even if we processed one input per second since the beginning of the universe, we still will be halfway through, and we probably won't find a match. But there are people that try to fasten this process, and some of them succeeded. This algorithm I showed previously, SHA1, is not advised to be used since, I think, 7 years, since 2010. The first attacks on SHA1 was prepared theoretical attacks were prepared on 2004. And since 2010, it's not advised to use SH1 because there were methods that could result in finding collisions. And just this year in February, Google found out the collision. They've created 2 different PDF files that have different content, but they produce the same hash output. And it took them this much of operations, and to compare that, it would take a single CPU 6,500 years to calculate that. But of course, they had many more of them. They had a cluster of many hundreds of processors, and they did it. If you want to read more about that, there is a page called shattered.it, and you can go there and see how they managed and how these PDF files look like. I think they have the same content, but the header is different in color, but the hash is the same. So that's the situation that we don't want to, and they proved that the SHA1 hash function is not safe. And now we'll go through some code examples. These ones are I've tried to select the most basic example. So this shows how the registration process could go and how the login process will go. So in this case, we'll go through the register user method. It takes object of user, and this user have, of course, a username, a password, etc. Going to the interesting parts. In this part, we're creating a random salt that I showed before that will be concatenated to the original password. In this case, it's random 16 bytes. In this case, we are executing our hashing function. This is the default method for the C#. It's recommended to use as an input 10,000 times. So it will go 10,000 times. So it will take the input, it will hash the output, and it will hash the output again and again for 10,000 times. This is also to prevent some attacks. For example, there are attacks that, based on the already cracked hashes, if you are cracking, for example, passwords, there are some default passwords like admin or password or 123, and these hashes are known, and sometimes can go through these known hashes and compare them. So this one is to prevent that. In this part, we are concatenating, as I said, the salt with the password, and in this part. We are converting the hash bytes because we are operating on the bytes. In this case, we are converting them to the string. And this part, we are adding this user to the database. The login procedure looks similar. So in this part, we are getting the user from the database. And we also convert it back from the strings to the bytes. We are converting the password. Here we are extracting the salt from the input, from the database. Here we are also using the hash function from C# to calculate the hash value of the input which we received from the login page. And here we are comparing each byte of the input with each byte of the received hash from the database, and if any of the bytes isn't matching, it's of course wrong password, and if all bytes match, then the password is correct. That's the one way that it could be implemented. The other way I propose is similar, but it differs in details. It's only about storing the password in one data table and the second one, and storing salt in the other database, just for the security reasons. If somebody would crack into our database and the salt and the password would be in the same database, that's kind of scary and dangerous. But if they are cracked in the one database and not in the other, then our stored hash passwords are pretty much safe. And the logging procedure looks quite similar, except for the salt is not extracted from the input, but from the other database. Last two reminders for the end. Like I said, don't try to creating your own hash functions. They are quite complex features to do, and we should just trust the people who do this professionally. It's not that bad to look up this code and use them, just adapt to our needs and we should be good to go. And also, we should be up to date with the standards because, like I showed, some hash functions become obsolete and shouldn't be used. So we should be trying to be up to date with the standards and looking up the most recent and most secure hash functions to date. So what did we learn, hopefully, today? I showed some theory behind the hash functions. We saw some example of usages where these hash functions are visible. We've looked into security of the hash functions, and some code samples were also presented. Are there any questions?
Is birthday, let's say, algorithm considered hashing function?
No, it's a method to crack the hash function. If we extend if we change the possible dates to possible outputs, then the statistics are not for.
Because it's not equally distributed during the year, so.
No, I don't think it should be used as a hashing function.
Do you have any experience with, let's say, tries to break your hashing functions in your everyday day-to-day job work?
No, actually I didn't. I only observe the users which are logging in. I of course only see the hashed passwords, but if they match character by character, then I know that these two users have the same passwords. And I sent this kind of email some time ago that you have the same password as the other person, and please change it because it's not safe for you.
But you don't mention the login of the
No.
How did you know the passwords are the same?
I've just looked at their hashed values.
Ah, right. Okay. Good, right answer. Excellent, thank you. If anyone else does have any questions, Rafal will be in the coffee area.
Yeah.
And for those who want to go and grab your coffees, then please do. Thank you.
Thank you.